Assignment 20, question 33, which is giving you the structure of aspirin. And it wants you to find the molecular formula, I believe, of aspirin. So this question is really whether you can differentiate between stick drawing here, where we're not actually labeling all the carbons or not adding all the hydrogens on there. If you can extract that information based on this method of drawing something. So we can start out doing this, and as we go through, I'm going to be touching on hybridization and geometry because I do think it's important. It's not mentioned in this question per se, but we have questions like this in exam, and I think some of you've gone over in class as well. So I'm going to point these guys out to you anyway as we go. So first thing, let's kind of look at the molecule and go piece by piece. So here, this one's nice and done, CH3. We know how many hydrogens are on that carbon. That's good. In terms of hybridization, so if you looked at the last question, question 13 solution set where I went through hybridization, it all has to do with electron groups. I'll touch on it briefly here, but I've written down the information again. You have 4 electron groups around a carbon atom. So think of it as 4 areas in space that are going to be occupied by something, an electron group. So either an atom, so this could be a single bond to an atom, a double bond to an atom, triple bond to an atom, all counts as one electron group, or a lone pair. Carbon in this case does not have the lone pairs. So in this case here, I have 4 electron groups because I have 4 different atoms or groups attached to carbon. So this will be Sp3. And geometry will be tetrahedral. Okay, here's a carbon atom. Is it missing anything else? Where carbon wants to be bound to 4 different things. So we have has 4 different bonds. Sorry, not 4 different things, 4 different bonds. 1, 2, 3, 4. I shouldn't call them different bonds. There's a total of 4 bonds. We have 4 bonds already on that carbon. So there's no hydrogens lurking that we haven't drawn out. That is complete. So think about now how many electron groups are on there. There are 3, right? This area of space, that area of space, that area of space. So that brings us to Sp2 hybridization. You're mixing your orbitals. Remember, S and 2 Ps give you 3 things, 3 electron groups. So Sp2, that's a carbon with Sp2 hybridization. And remember, Vesper, if it's Sp2 hybridized, 3 things in space spreading themselves out as far as possible. That is trigonal planar. This oxygen wants to have 2 bonds to something. And if we think back to Lewis dot diagrams, anytime we do anything like this in first semester, you're always going to have, generally, to have a neutral oxygen atom, you'll have 2 bonds and 2 lone pairs. So to complete this, really you have that lone pair set there. Okay, and there's your 2 bonds to add up to that octet of electrons around the oxygen. So nothing else on that one. Over here, same thing, oxygen, 2 bonds, 2 lone pairs. You already have the 2 bonds. Let's stick these lone pairs on there as well. So a terminal atom like this, we wouldn't really talk about hybridization at all, okay? This one here though, where it's in the middle of the molecule, bound to 2 different things, we can discuss hybridization. So think about how many electron groups are around that oxygen atom. You have 1 for each of these bonds coming off, and then 1 for each of these lone pairs. So this is 4 electron groups. So that hybridization there is Sp3. Now going back to geometry, do you remember we had electron group geometry versus molecular geometry? So electron group geometry had to do with the total number of electron groups, which was your hybridization. 4 areas of space means that this is electron group geometry, tetrahedral. And molecular geometry is what you're actually going to see though. So you're only going to see the atoms. You're not going to see the lone pairs, but they're there and they're forcing this other geometry. So if you kind of ignore the fact that you have those lone pairs there, what you're seeing is a bent geometry. So it's important to go back and kind of remind yourselves of this, but there's our oxygen. This carbon here, now this brings us to this way of drawing a benzene ring, which really comes from, what that means is that you have this resonance between the way you've drawn out your double bonds. Okay? Because these electrons, there's 6 electrons total here, and these double bonds are delocalized throughout the entire ring structure. And as such, we draw a circle instead of having this drawing the resonance out in each case. But this is what each one will look like. So each of these carbons, this carbon here, will have a double bond, a single bond, and it's bound to up here as well. So each of the carbons in a benzene ring like this is sp2, has 3 electron groups. So all of those ones, let's say all carbons here are sp2, trigonal planar, which means entire benzene is flat, nice planar molecule. This one has no other hydrogens on it because it already has, say, a double bond, single, single. This one, however, if you think about it, there's a double bond, single bond, it's missing a hydrogen here. So there is a hydrogen atom. And in fact, there's a hydrogen atom on each of these carbons that has nothing else on them. Okay. This one here, though, same boat as that one. So you have a double bond either here or here, single and single. Okay. Up here, here's another carbon, another sp2. You're starting to recognize double bond, single, single. sp2 hybridized, no more hydrogens on there. There's that oxygen with some lone pairs. Same with this guy here. Lone pair bound to an H. Same situation as this one here. Okay, we're not missing anything else on there. It's showing the H, so that's good. Okay, if you're to add all this up now, what are you gonna get? And I've kind of destroyed our picture here, but in terms of carbons first, 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. So C9. Count up our hydrogens. We have 3, 4, 5, 6, 7, 8. And how many oxygens? 1, 2, 3, and 4. I'm not going to do part B of this. Part B just has to do with calculating moles from mass, knowing molecular weight. This is what you need to get the molecular weight, and then you can easily do that part of the question.